All right, folks, here we are. We have made it to the Phanerozoic Eon, and the first era of the Phanerozoic Eon is the Paleozoic era. So look at how far we've come. I like to take this like 5,000 foot view at the beginning of every chapter so we can see that we have covered 21 of 24 hours of the geologic day, and we have begun our discussion now of the Phanerozoic Eon, which is the eon of visible life. And the first era in the majority of the Phanerozoic Eon is comprised of the Paleozoic era, which is 6.5% of all of Earth's history, and is covered in chapters 10 through 12 of your book. So the other thing I want to talk about is just kind of an overview of the Paleozoic so we can see where we're going. And this is a slightly different geologic time scale. This geologic time scale only focuses really on the Phanerozoic. And so you can see this, and this is from your textbook, breaks it, well, you can see it's referenced in SLOS as well, but it breaks the Paleozoic into the early Paleozoic and then the periods of the later Paleozoic. So you can see that that the Phanerozoic is broken down into the Paleozoic era, the Mesozoic era, and the Cenozoic era. And then each of those eras are subdivided into these geologic periods. So we're going to be starting our discussion with the Cambrian, go through the Ordovician, the Silurian, and then into the Devonian, Mississippian, Pennsylvanian, and Permian eras. No, periods. They're periods. Sorry. Okay, so these are the periods of the geologic timescale in the Paleozoic. A quick overview is when we think of the Paleozoic, we start to think about a rich fossil record, because the fossil record in the Paleozoic is really important and begins really with the onset of the Cambrian period, as you'll see in just a few minutes. So this geologic timescale shows you that in this column here there were 4 major orogenic events that occurred in the Paleozoic, and we'll be talking about those: the Taconic orogeny, the Acadian Caledonian orogeny, the Antler orogeny on the west coast, and the Alleghenian orogeny. These other 3 orogenies, 1, 2, and 4, have to do with the formation of the Appalachian Mountains, and then the Antler is the beginning of onset of the Rocky Mountains in the western U.S. There are 4 major transgressive cycles, and that's what's colored in green here. And so if this were the center of the craton or the continent and this were the margin, you can see that in not a very smooth pattern that the sea transgressed over North America in what's called the Sauk transgression, and then you have a large regression followed by the Tippecanoe transgression followed by a regression. And it's not random that these major regressions correspond with major orogenic events. Then you're followed by the large Kaskaskia transgression and regression that roughly coincides with the Alleghenian orogeny, and then finally the Absaroka transgression as well in the Paleozoic. Finally, the Paleozoic is characterized by 3 of the 5 mass extinctions that we see in the Phanerozoic Eon, beginning in the Ordovician period, another one at the end of the Devonian period, which we're not going to talk about too much, but then we'll spend a great amount of time talking about the mass extinction that ended the Permian period and also then ended the Paleozoic era. So without further ado, let's take a deeper look at the early Paleozoic, which is covered in chapter 10 of your book. And your book follows along in chronological order, so it'll begin with the Cambrian period. So when we have geologic changes in the geologic timescale, they often coincide with a significant event. And the Cambrian period is identified in the geologic record by the first occurrence of the trace fossil Trichophycus, which is represented here. If you were in class with me right now, I would make you say Trichophycus out loud, so I hope you say it in your home. Trichophycus is a great word. It is a trace fossil, and it doesn't look like a whole lot, but it shows complex motion. So it shows that this organism that created the Trichophycus trace fossil could move both laterally and horizontally, presumably looking for food. And the Cambrian is marked by a period known as the Cambrian Explosion, which sounds very exciting. It's a period where, if you just look at the rock record, it looks like there's a really rapid diversification of life on Earth. Really, what the Cambrian Explosion represents is a time period when organisms evolved the ability to generate hard parts. Hard parts include bones and teeth and shells, and they are enormously important for the fossil record. The fossil record, well, here's a reconstruction of the Cambrian period. The fossil record is incredibly biased. Your odds of being fossilized are less than 1%. Although I think that there's like a location in South Dakota where you can have your remains sent after your untimely demise, and they say they will turn you into a fossil, but they don't go into a whole lot of detail on their website, so I'm not totally sure what that means, but it sounds like a very exciting follow-up project. So who is the fossil record biased towards? Well, it's biased towards certainly organisms with hard parts. Jellyfish do not fossilize well. They don't show up regularly in the fossil record. It is biased towards organisms that live in shallow water environments, because as sea level will rise and then fall, the rocks deposited in those shallow water environments will become available for human exploration much more readily than rocks under the sea. And it is biased towards organisms that are rapidly buried by sediment, because what will happen is with a lot of these creatures, they will be broken apart by waves, they will be scavenged by other organisms, and so your potential for fossilization is high. Then if you have hard parts, if you're in a shallow water environment, and you can be rapidly buried after your death. We don't know about probably the majority of organisms that have ever existed, which is that's a daunting thought, but it's pretty cool. So why did organisms suddenly develop the ability to have hard parts in the Cambrian? So there's a couple contributing factors, and this is hypothetical because this is one of those events that occurred in Earth's past, but then not any longer. If you recall, the very end of the Proterozoic was the end of snowball Earth, and afterwards oxygen levels were significantly higher, pretty similar to what they are today, about 21% oxygen in the atmosphere. So the other thing that happened towards the end of the Proterozoic eon was the evolution of eukaryotes, organisms with complex cells and cell walls and lots of different organelles. Well, eukaryotes thrive off of oxygen in the atmosphere, and this high inconsistent level of oxygen in the atmosphere led to likely a diversification of eukaryotes as they moved into a time period when the Earth was set up pretty well for them. The second thing that happened in the fossil record that we see represented, like in this particular trilobite sample here, is the evolution of eyes. And trilobites had complex eyes, so they were like spiders, and that they were crazy, like segmented eyes. This was an important strategy for a predator, which trilobites were. Some of them were. And so, right, eyes, if you see your prey, it's much easier to eat them. But then similarly, once eyes show up in the fossil record, it's much harder for something to eat you if you have a crusty shell. And so organisms that did start to develop these more resistant exoskeletons were harder for their prey to eat them. And so it was an important evolutionary strategy for soft-bodied organisms. So it was an evolutionary adaptation. Another thing that happened around the beginning of the Cambrian is the erosion of some mountains that are referred to as the TransGondwana mountains. So Gondwana is a series of continents. It wasn't a supercontinent because it wasn't composed of all land, but you can see that it was composed of South America, Africa, the Arabian Peninsula, India, Australia, and Antarctica. North America, we can see over here, is part of Laurentia, and it is connected with parts of Baltica here in a chunk of land that geologists refer to as Laurasia. which would be a cool name actually for a human. I'm going to rotate this model of Gondwana quickly so you can kind of see where the Gondwana Mountains were. They were formed at the suture zone between Africa, Antarctica, and India and parts of the Middle East. And the weathering of the TransGondwana Mountains resulted in lots of continental erosion and transport of calcium from the weathered rock into the seawater. And if you recall, most hard parts from organisms are calcium carbonate. And look at that's what we got here. We got calcium being shed from the rocks on these mountains and eroded, carried to the sea by rivers, and then being available for organisms to use for their hard parts. So this is kind of let me go back here so we're focusing. This is kind of a cool idea because it means that that organisms under a time of stress were able to figure out how to use what was essentially just like chemical garbage and use it to make hard parts in a way to protect themselves. And we see that actually throughout the Phanerozoic is that the organisms that end up surviving challenges to their existence very often will figure out how to make things work in kind of lousy circumstances and figure out how to make something out of nothing, basically. So that's what these organisms did. The fourth, whoops, now I have to go the right way. The fourth, there we go. Sorry about that. The fourth postulated cause of the Cambrian explosion is high rates of seafloor spreading. And the reason is that seafloor spreading at divergent boundaries releases also some calcium into seawater at mid-ocean ridges along vents. I do want you to know that this one is the most hypothetical. We don't have any seafloor really left from the Cambrian period. And so that estimating seafloor spreading rates for 500 million years ago is a bit of a challenge because we don't have any of that to tell whether seafloor spreading rates are any faster than they were today, although they likely were, since we're talking about 500 million years less of cooling of the core and less radioactive decay of isotopes. But again, that is purely hypothetical. We'll talk about another period in the Phanerozoic when there was high seafloor spreading rates, and we can actually document that in our next unit. So we know so much about the Cambrian explosion in part because there is good preservation of some of the fossils, but there also are some exceptional rock layers. And we're going to learn first today about the Burgess Shale, which is exposed in British Columbia and was deposited approximately 530 million years ago, so at the very earliest of the Cambrian explosion. It is what is known as a lagerstätten, which is a great word. A lagerstätten is a rock layer that has exceptional preservation of fossils or preserves exceptional biodiversity. And this is a bit of both. And we're going to watch a video of the Walcott Quarry, I believe, where the Burgess Shale is exposed in British Columbia. It is definitely on my bucket list.
Join us for a guided hike to the Burgess Shale in Yoho National Park and spend a day with a Parks Canada interpreter. So one of the things that we'll see when we get up to the quarry is we'll see a real amazing diversity of body plans. So we see creatures that were predators, creatures that would have been scavengers, creatures that were at the very bottom of the food chain, and animals with all kinds of defensive techniques. A visit to the Burgess Shale is very special because you really get to be hands-on with the rock, to step into a little bit of history and see some spectacular fossils and do it in a fantastic surrounding. I mean, one of the most beautiful spots on the planet. So the mountains are young but falling apart, but the Burgess Shale fossils are ancient, 500 million years old, and still perfectly preserved, waiting for us to come and see.
This is more than what I expected. I didn't really expect that much other than a long hike, but it has its benefits, and it's definitely been nice to stop and enjoy the scenery, and especially to get up here and kind of look around for fossils and stuff like that. I mean, you really feel like you're doing something, and you're not just behind a velvet rope. You're really touching and feeling it, which is it's really fun.
I'm very surprised that they are so much and that they are so old, and you can see them everywhere.
You just sit here and pick up a rock and there's a fossil. You just look here and there, and it's beyond what I thought it would be.
It's amazing. It's almost humbling that this, 500 million years old, and it's still here, and we can see it and experience it. And this is the start of life. That's you and me today. Yeah, you expect to see maybe half a dozen, and they're just everywhere, all the fossils.
For more information, visit our website at pc.gc.ca/Burgess Shale.
Good stuff. So here are some of the fossils that are preserved in the Burgess Shale. What's crazy is that these fossils were almost like just squished, and with really almost like millimeter level precision. They can have these fossils can be excavated and then almost like an accordion that is unfolding, kind of be reconstructed. So this is a fossil of an organism called Morella that likely looked like this in the Cambrian Sea. This is Choya, which you saw earlier in our reconstruction from the Cambrian explosion. This itty bitty creature was about 10 centimeters long and crawled along in the seafloor. I'm sorry if you can hear my dog snoring. He's really tired today. And I'm not going to pronounce that name. This is Otoya, which was a burrowing organism, and moved through the Cambrian sediment like you see illustrated here. This is Wawaxia, and that's a cool looking organism that was epibenthic, so it crawled along the seafloor. Pretty fun. This is the big predator of the Cambrian Sea. It's called the Anomalocaris. Actually, it's really scary looking. I'm not going to pretend. So these guys could get between 3 to 6 feet in length. And yeah, so you can see we've come a long way from stromatolites to the Cambrian explosion. Here we have Opabina, which also sort of reminiscent of a cross between like a lanternfish and and some sort of a slug, really. Hallucigenia. I'm sorry, I keep forgetting to take that sound effect out. Hallucigenia is so cool. This was a meme I saw on hallucigenia, and no one really knows anything about hallucigenia other than it probably walked in along the seafloor in sort of an epibenthic matter. But yeah, what a creepy, crazy organism. So these are preserved in the Burgess Shale. You can't just show up at the Wolcott Quarry and hike up to it. You need a permit. It is protected by it's a UNESCO site, so it's protected by the UN. And again, one day I'm going to make it there. And it's only accessible really in the summertime. So those are our main events of the Cambrian. Next, we're going to talk about the Sauk transgression. So the Sauk transgression is a eustatic or a global transgression across Laurentia. And it's recorded when we look at some of the basal units of the Grand Canyon. So you'll be doing a little exercise after this lecture on the Grand Canyon. But here we have the Vishnu schist and the Zoroaster granite that are exposed at the base of the canyon, and we can see that there's a non-conformity here between that and the Tapete sandstone. And then we see the transgression of sandstone to the Bright Angel shale to the Muov limestone and then dolomite. So that Sauk transgression can also be mapped across most of Laurentia by looking for sand deposits. So sand is illustrated here in this purplish stipple color here. So this shows you actually right where the shoreline was, and there's been a little bit of erosion here, but you can see this is where North America's seashore was. Everything colored in yellow here would have been underwater, but you can see that the vast majority of North America is underwater, and we determine the paleo shorelines by the location and correlation of sandstone deposits across North America at this time period. Pretty cool, big old transgression that ends in the Ordovician period. The Ordovician period is a time period where we have lots of different things going on. We have our first orogeny of the Paleozoic called the Taconic orogeny. The Taconic orogeny occurred where we have collision of Laurentia with an island arc. And so here we have that illustration of North America or Laurentia. And then we have an island arc that is slowly sort of subducted, the ocean crust beneath North America, and this island arc is slowly subducted. There is the accumulation of accretionary wedges, which sometimes, remember from an earlier unit, contain ophiolite suites, which are kind of cross sections of some of that ocean crust that becomes accreted into that accretionary wedge. And then this accretionary wedge ultimately becomes part of North America and what is called, if you ever heard the Taconic Highlands in New York, that's part of that ancient accretionary wedge. So in this paleogeographic map, you can see this very long island chain, and this long island chain was then accreted as the ocean crust between them was subducted, and it became accreted onto the east coast of North America. We can identify some of these rocks by looking at the faults that are associated with, for example, the Taconic Highlands. And if you look, these are by and large reverse faults, which are high angle faults where the hanging wall or the top block moves up and over the foot wall. Sometimes we have those faults which are at a lower angle, and those are called thrust faults again. So when you have those shallow angle reverse faults, those are called thrust faults. And this is the first of the in the Paleozoic anyway, the first orogeny that helps to contribute to the formation of the Appalachian Mountains. These types of faults can be recreated in sandbox experiments. Are actually super cool, which you'll see here from Union College. So sandbox experiments are pretty much where sand is poured into a plexiglass, and then you have, in this case, a block, and it's slowly compressed, and as it compresses, you'll see some of those faults form. Oh, Curtis Brewer brought the popcorn. So the sand in this box is initially deposited horizontally, and then you have compression of the box, and you start to see the creation of both thrust faulting and reverse faulting. So I'm pretty sure they're going to zoom in on this. The blue represents deposition, while you have this convergence and faulting. So one of the things, I want to pause it right here, is that you can see that some of these rocks have been completely overturned. And that is definitely something that we see in that Appalachian Mountains today, where this rock layer, in particular this red layer here, has been completely flipped upside down. So we have a series of thrust faults and then more high angle reverse faults when we have this sort of compression. All right, so the Taconic mountains, as they're uplifted, are also being eroded, and they erode into a piece of land that's called the Queenston Clastic Wedge. So here is a map showing you the location of the Queenston Clastic Wedge. So the orange area shows you your area of primary compression. And so here's where your Taconic mountains are, and they are eroded, and as they are eroded, they shed sediment into this sort of back arc basin, and they accumulate in this apron shape region called the Queenston Clastic Wedge. We're going to talk about another Queenston Clastic Wedge, and I'm going to be honest, I always remember that the Queenston Clastic Wedge goes with Taconic Mountains by remembering QT, like it's a cutie of a clastic wedge, I guess. I don't know. It just helps me to keep it straight, because you're going to see that there's a lot of like just information to keep straight. So as we take a cross section from New Jersey all the way over through Michigan, we can actually see the Queenston Clastic Wedge, where it's basically just sediment that's shed from the Taconic Mountains, and it fills this large back arc basin, and we can see that there has been isostatic subsidence here, right? Because as the basement rock is eroded and shed into this back arc basin, the weight of this sediment pushes the basin downward. And that's also reflected when we look at an isopack or a thickness map of the Ordovician sedimentary rocks that are shed in this location. So here we have our Taconic Mountains. This is our source area, and they are shedding sediment into the back arc basin, and then it is subsiding under its own weight because there are over 2,500 meters of sediment that are eroded from these mountains at this occasion. All right, we're going to take a pause, and you're going to do an activity on the Grand Canyon and have a little discussion before we pick up with our conversation on mass extinctions in the Ordovician. All right, have fun.